earlier when we were developing the equations for the Lagrangian formalism, we said that the generalized forces were expressed as q I, and that has three components, three possible types of forces. One, the forces of interaction between mass points through capacitive elements. So, of interaction through capacitive elements. The second possibility is the externally impressed forces. So, and third possibility is the forces due to friction. Out of that, these two, we say that these two can be obtained from a suitably defined potential function. So, that is how we proceeded, and when we did so, we wrote the q I is minus. So, that is how we proceeded, right. So, this was just to recapitulate where we were. So far we have only taken into account these two types, and we have not yet accounted for the forces due to friction. So, that is what we will try to do today. So, the objective today will be somehow to include the forces due to friction into the q I term, but there is a problem here. The problem is that while the other forces could be obtained from a potential function by partially differentiating the potential function with respect to a the generalized coordinates q I, obviously that cannot be done for the friction. Why? Because the frictional force, say I have something moving against, say this one is moving against a surface like this, then the force due to friction, if it is a not a dry friction, then the frictional force is proportional to what? The velocity. Therefore, there is no way that you can express that as a function of v, because after all what you are what is its what is dependent on? It is dependent on the velocity, not the positions. Okay. So, that is a problem. So, in general, if the coefficient of friction is say r and the speed of motion is q I dot, then I know that the force will be r I q I dot. Okay. So, force due to friction where obviously I is the ith generalized coordinate, ith direction. In that direction the velocity is q I dot, and on that we have to multiply the force coefficient, okay, frictional coefficient. So, this is the expression. Obviously, that cannot be obtained like this, but still we would like to, we have already seen there are many advantages of the Lagrangian formalism which we do not want to give up. So, somehow this feat has to be obtained, that we want to include this into the Lagrangian formalism. Rayleigh proposed that this can be done by defining a new type of potential which is obviously velocity dependent. So, velocity dependent potential that would be expressed as half r I q I dot square along each of these directions. So, total Rayleigh potential is I will express the R Rayleigh potential in order to distinguish it with it from this force coefficient R by some kind of a script R, that is equal to summation over the number of generalized coordinates. That was the proposition of Rayleigh. Therefore, this is called the Rayleigh potential. So, what are the properties of this potential? This potential is firstly not dependent on the coordinate, it is dependent on the velocity. The second property is that if you differentiate this with respect to q I dot, what you get? That is what we wanted. Okay. We wanted to obtain the force, and that is what we obtained, which means that this Rayleigh potential, when partially differentiated with respect to the generalized velocities, give the force. All right. Now, recall how we proceeded to obtain the Lagrangian function. At some stage, if you go back to the page in which you have written down where I was deriving the equation, there was one stage where you have dt of partial derivative t with respect to q I dot minus partial derivative t with respect to q I plus partial derivative v with respect to q I. Okay. Oh, sorry, at this stage it was minus q I equal to 0. Okay. And then we had substituted this by this, right. So, this is where the generalized force term appears, and so long as there is no dissipative term, no friction term, no resistive element in electrical circuit, this term only contains it can be obtained from by differentiating the potential function V. That is how we proceeded. But now we find that in the new framework where we need to include the resistive things, then you q I earlier was expressed as this only. Now, it has to include in addition so if this is the new term, that means this was due to the conservative forces and this is the non conservative forces, then these together give you the q I term. Substitute it here, you have dt of here we have the right, and here will be and then we had argued that since the V does not depend on q I dot, therefore, I can also write this as the Lagrangian term. So, we will continue with that argument, we will say here is the Lagrangian minus here is the Lagrangian, sorry, this q I plus the Rayleigh term with respect to q I dot. So, this will now be the modified Lagrangian equation that takes into account the dissipative forces here. This is the additional thing. By the way, before we proceed, I would draw your attention to something that we have said, which sort of one tends to take for granted. We said that this to this is possible only when I will write it here, only when fine, because actually it was the partial derivative of t with respect to q I dot, but we had replaced it by in order to simplify the notations by the Lagrangian with respect to q I dot, and that assumes that the other term is 0. Now, naturally this will be valid when this is true. I will cite you some examples where this is not true. There can be situations like that. Now, when that is observed, then you will have to take this equation into consideration, not this. Just this pointer, just keep in mind. Fine, let us now see a few examples of how this could be done. This can be done in a practical system. First, consider, we had already considered this system a two-dimensional oscillator there are two position coordinates q1 and q2. Okay. We had said this was k1, this was k2 and this was k3, and this is the wall, this is the wall and this is the base. Earlier when we are solving this problem, we say that these two surfaces are perfectly frictionless surfaces, but now let there be friction. Let us see how would you do it.
Sir, in this case when we had conservative forces,
Yes.
We took qi as minus dv dqi, right?
Yes.
And for frictional forces, where frictional forces del r del qi. Dou r dot qi.
Here.
Qi dot.
Yes.
So when we write qi, won't it be minus dou v dou qi plus dou r dou qi dot?
Okay. So, his question, let me repeat for the sake of the microphone. His question would be was that since if you differentiate it you get this, therefore, should it not be plus? Okay. Is that the question? Yes. Now, you notice that ultimately we want to get the signs right. Signs right means here is the equation in which the force must appear in the proper direction. Now, in order to have this force appear in the proper direction, since this was negative, therefore, I had to have this as positive, this as negative, so that ultimately we get it positive. This will be clearer when we actually solve the problem, and then you will be able to check whether this particular force term has the right sense or not. If it has, then this is okay. If it does not have, it is wrong. Okay. Let us check that. So, we had come to this problem, and since we had already done this except for these two, suppose here the frictional coefficient R1 and here the frictional coefficient is R2. Then we had solved the problem except these two. So, just recall that and then let us add, otherwise we will unnecessarily lose time writing things. So, we had already written the kinetic energy, the potential energy, they remain unchanged, only what is added is the Rayleigh term, which is half R1, R1 is acting along the q1 dot direction. So, q1 dot square plus half R2 q2 dot square, fine. So, that the dou R1 dou R dou q1 dot is R1 q1 dot and dou R dou q2 dot is equal to R2 q2 dot. Happy? Then after that we just recall what was our expression for the T and V. You already have it. Let me write down so that we can derive the whole thing. T was half, this was m1, this was m2, m1 q1 dot square plus half m2 q2 dot square. That was the expression for the kinetic energy. The potential energy expression was, potential would be for this spring, this spring, this spring, and no gravitational potential. So, it was half k1 q1 square plus half k2 q1 minus q2 square plus half k3 q2 square. This would be the potentials due to the 3 springs. At that time we had considered there is a application of force. Where was it? On this mass. So, there was a force. That force will be, since it is in the same direction as q1, therefore, I would have to write it as minus f q1. That is how it was, right. And now you have included this new term. And now do the proper differentiations and write these equations. Do this. These will have to be written in both q1 direction as well as the q2 direction. So, is it visible? Yes. I can see that in the q1 direction, I will write the Lagrangian differentiated with respect to q1 dot will be only this. So, m1 q1 double dot, that is the first term. The second term would be this, where I will be interested in, okay, let me write down the Lagrangian, else it becomes problematic. This minus this, half m1, right later. So, that was the Lagrangian function, Rayleigh function is there. So, if you now differentiate in the first direction, you will get in the q1 direction you have this k1 q1 plus k2 no, okay, and the Rayleigh terms derivative was this. So, my final expression becomes m1 q1 double dot plus k1 q1 plus k2 q1 minus q2 minus f, right. Then I have to include this term plus r1 q1 dot equal to 0. Now, let us see, is it right? First, let us write down the second equation also. The second equation would be m2 Q2 double dot minus K2 Q1 minus Q2 plus K3 Q2, this will not be there, then plus R2 Q2 dot. Okay. Fine. So, you see these are the expressions, and let us get back to the picture. Can you see? Yes. Force, if you take the other side, force is acting in this direction and this fellow is moving in this direction. So, force is equal to mass into acceleration here. Force will have F in this direction minus K1 Q1 pulling in this direction, K2 Q1 minus Q2 in that direction, all right, and this fellow. So, if you bring it to this side, F will be positive and this fellow is negative. So, this is acting in the direction opposite to the force, this fellow is moving in this direction. So, this is also acting in this direction, right. So, that has got the sense correct. Fine. So, these are then the final two equations for these coordinates. I would later consider how to handle this, tackle this, how to solve this, those things we will handle later. But at this stage we are only obtaining the differential equation. So, this is one good example. Let us for this system, can you visualize what will be the electrical equivalent? We had already seen there will be two resistances. So, we have already seen that the representation of this would be the two masses will be represented by inductors, the springs will be represented by capacitors, and this force will be represented by a battery, and there is a resistance that shares the same motion with this mass, the inductor. So, you have, so this is the equivalent of this mechanical system. If you obtain the equations for this electrical system, you will get exactly the same equations, only the K and 1 by C will have to be interchanged, that is all. Now, let us solve one typical electrical circuit problem to illustrate how this method helps in obtaining the electrical circuits. Let there be resistance here, let there be another resistance here, let there be capacitance here, and let there be a voltage source here. Okay. The differential equations of this system, that is what we would like to obtain. This is our E, this is L, this is C1, this is C2, this is R1, this is R2. First, how would you decide what are the generalized coordinates? The minimum number of potential coordinates that we can identify. No, not potential, charge, because the equivalent of the position is charge. So, I want to identify what are the independent directions of flow of charge, and from uh, the first year circuit theory course you have learned that if there is a circuit like this with, we have to first identify the windows or mesh, and the number of minimum number of variables necessary would be the number of meshes. So, it will be very convenient to identify the 3 meshes like this. Okay. Then we will say this is our Q1 direction of flow, this is our Q2 and this is our Q3. Okay. Once we have done that, we can then proceed to write the kinetic energy and the potential energy of this circuit. What will they have? First, the kinetic energy T. Kinetic energy will consist of the energy stored in the inductor and the energy stored in the inductor, this inductor, and the charges flowing are Q1 and Q2. Therefore, the current flowing through this is Q1 dot minus Q2 3 dot. So, this is what produces the stored charge. So, you have half L Q1 dot minus Q3 dot square, and that is the only place where kinetic energy could be stored. The potential energy is the energy stored in the 2 capacitors. So, let us take this one first. It will be half 1 by 2 C, C is in the denominator, 1 by 2 C, this is C1. The charge flowing is Q1 minus Q2. So, Q1 minus Q2 square. In this one it is C2, it is Q3, plus there is something here. This is the externally applied force which is acting in the positive direction of Q1. Therefore, you will have to say minus Q1 E. Okay. So, that is the potential energy, and the Rayleigh function would be here. For this one it would be half R1, then I have to identify what are the currents flowing through this. It is Q2 dot minus Q3 dot, right. Q3 2 dot is flowing this way and Q3 dot is flowing the opposite way. So, Q2 dot minus Q3 dot square, and this one plus half R2 Q2 dot square. The moment you have written this, the rest is trivial, right. So, all you have to do is to differentiate these 3 functions. So, let us write the Lagrangian. It is, I will write fast, half L Q1 dot minus Q3 dot square minus 2 C1 Q1 minus Q2 square minus 2 C2 Q3 square plus Q1 E, and Rayleigh is this. So, the first direction Q1, in the Q1 coordinate, the what do you have? Minus Q1 by C1, Q1 minus Q2 by C1, yeah, okay. is L into q1 dot q3 dot, and your Rayleigh function is, notice the Rayleigh function, yes, it is independent of q1, 0. So, now if you write the equation, you will it will be, so the equation is d dt of this, which means L q1 double dot minus L q3 double dot, then this one negative of this one q1 minus q2 by C minus E. Okay. This term, the Rayleigh term is 0, therefore, this is okay, fine. Let us do it in the direction of q2 also, because that illustrates the use of the Rayleigh term. In the q2 coordinate, what we have, q2 is this one, we are differentiating, this one we are, can you see, yes, this one we are differentiating with respect to q2. So, you have plus and nothing, Lagrangian with respect to q2 dot is 0, and delta r with respect to is, it was here, yes, it will be r1 q1 dot minus q3 dot sorry, yes, and the other term will also remain. Now, if you write down the equation, it will take the form this is 0, therefore, d dt of this does not exist. So, you will have minus of q1 minus q2 by C, okay, plus r1 q2 dot minus q3 dot plus r2 q2 dot equal to 0, right, done. Similarly, you obtain the equation in the third direction, and it will actually take the form L q1 double dot minus q3 double dot plus 1 by C2 q3 plus L sorry r1 q2 dot minus q3 dot. So, the three equations are this and where
in the q3 direction it will be minus L q1 double dot minus q3 double dot.
this one,
Yes, sir.
let us check.
With the minus sign.
Sure. Yes. Wait. This term, since you are differentiating this, there will be a minus term here, and the third term will also, yes, minus. Okay. See, in this case, no, I should actually write explicitly, otherwise this is creating problems. So, the Lagrangian with respect to Q3 dot is, notice the Lagrangian, it will be L times this, but now this has to be differentiated. So, it will be minus. So, minus L Q1 dot minus Q3 dot. The derivative of L with respect to Q3 is Q3 only here, minus Q C2 Q3, sorry, and then here again it will lead to a minus. So, R1 Q2 dot minus Q3 dot, and the second it will lead to a minus sign. So, minus R1 Q2 dot minus Q3 dot, and this is 0. So, now the equation becomes minus L Q1 double dot minus Q3 double dot, derivative of this with respect to time, this plus 1 by C 2 Q3 plus or minus R1 Q2 dot minus Q3 dot. So, that is the equation then. So, you have the 3 equations. Where are they? Where are the 3 equations? Okay, this is the Q2 equation, this is the Q3 equation, and where was the Q1 equation? Here, right. Now, notice one thing, what is this equation actually? Notice carefully, what does it say? Look at the circuit. No. Can you see this too? No. No. Anyway, look at this circuit and you have already written down. So, tally, what does it say? L Q1 double dot minus L Q3 double dot. So, it is actually L di dt, where I is Q1 dot minus Q3 dot. Here is the voltage across the capacitor Q by C, and here is the E. So, this is nothing but the KVL, right, which means though we have not derived the Lagrangian equation using the Kirchhoff's laws, it is actually consistent with the Kirchhoff's laws. So, when we obtain a differential set of differential equations, we can also start from the Kirchhoff's laws and do it, no problem, and you will not be forced to do it this way. But you will find that for many systems, since I do not have to worry about the direction of this for example, because it is squared, I do not really care which direction is positive, which direction is negative. It is far more advantageous in terms of writing down the equations correctly. And later we will also illustrate a more suitable method for specifically devoted to electrical circuits, but you can easily see that the set of equations that we develop using mechanical systems as example are equally applicable to electrical circuits, and they are not contradicting the Kirchhoff's laws, which you know to be correct. Okay. Similarly, you can check that the second equation will be actually the KVL equation, Kirchhoff's voltage law equation, in the Q2 loop, and the third one is along the Q3 loop. Okay. Only one pointer, that is, I do not know whether you know this, that we had started by the assumption that we can define the minimum number of necessary coordinates by simply looking at the windows and putting the q1, q2, q3 along them. This is in general true, but there are situations where this is not true. There are situations where this procedure does not give the minimum set of coordinates. That gives, you can always define that way, all right, it will not be wrong, but that will not give you the minimum set of coordinates, and how to write down the minimum set of coordinates, that is a problem we will take up later. Just a pointer that this works and what you get is right, but that is not the minimum thing. Okay, let us carry on. Fine. So, we have learned how to use it. Can you just quickly write it for this system? Say there is a mass, there is a spring, there is a damper, there is another mass, there is a spring, there is a damper, and now it is connected, it is resting on the ground. Okay. And now you apply a force. Can you write down the differential equations for this system? Do this first, you will need to define the coordinates. How will you define the coordinates? Position coordinates of these two masses. And if you want to define the position coordinates of these two masses, you have to specify what is their 0. So, you cannot simply say that here is my position and then this is say q1 and this is say q2. Yes, you can say that, but the moment you say, you will have to say where is my 0. Now, let that 0 position be where these two springs are relaxed, no energy stored in the springs. So, the q1 and q2 will directly give the amount of energy stored in the spring. So, you can easily see that if you do not apply any force, let it rest, then these two springs will come to a compressed position at rest, and that is not what I am defining as the 0. Why? Because in that case, how much has it been compressed initially and all that we have to consider. We say that let these two be measured from their 0 position, where in the 0 position there is no energy stored in the springs. Quickly.
So, we take the masses different.
Oh yeah, m1 m2. So, let this be m1 and let this be m2. Now, if you proceed to write, first you will write the kinetic energy, which is somewhat trivial, half m1 q1 dot square plus half m2 q2 dot square. Fine. Potential will be the potential stored. Okay, for now let us ignore gravity, because ultimately if you consider gravity, it will lead to constant terms that will be differentiated away. So, who cares? I do not want that. So, V will be due to the two springs and the force. So, it will be half, let this be k1 and let this be k2 and this is be r1 r2, half k1, then how will you write? No, q1 minus q2, right? q1 minus q2 is the amount of displacement experienced by the spring. So, q1 minus q2 square plus yes half k2 q2 square. Yes. Now, here you see q1 is up and f is down. So, we will say plus, no, just q1 is acting in the direction of q1, right. Then your Lagrangian becomes, I will just quickly write so that we can differentiate first. What I will write? Okay, now the Rayleigh function, it will be, what is the relative velocity experienced by this r? It is q1 dot minus q2 dot. So, it is half r 1 q1 dot minus q2 dot square, and how much is the, is only q2 dot, for r2 it is only q2 dot. So, it is plus half r2 q2 dot square, right. From here, do I really need to, the rest is trivial, right. The rest is trivial, and therefore, I leave it to you. You can, you know how to do it. See, you notice that the actual thing that you have to do is to write these two, nothing else. The rest is so algorithmic that you do not really need to bother about it. You only have to do the differentiations right, which I suppose you learnt in school. So, this is rather simple way of doing it. By the way, this actually represents physical cushioning system, cushioning system where cars and motorcycles, they have a cushion, so that you do not directly feel the vibration on the of the earth, and these are somewhat like that. You may have seen this arrangement in the back, around the back wheel of the motorcycles, right. You get a cylinder in which the friction and spring arrangement is there. So, exactly this kind of arrangements in order to dampen or cushion your the rider's motion. Fine. Now, let us come to another issue. You might notice that we have okay, where was the circuit I was dealing with? Okay, circuit, it is not necessary, we can again do the circuit. There may be a number of inductances in the circuit, and if there are number of inductances, there may also be mutual coupling between the inductances. What happens then? If there are two mutual inductances, there are two inductances, there is a mutual coupling between them, then how does it get reflected in the equations, and through what? That is the question let us deal with. So, let us take one example circuit, simple one. This is the positive direction of the voltage E. Here is say an inductor, and here is say another inductor, and the rest of it can be connected through resistive and capacitive branches. Okay. So, you have L1, L2, C, R, but now in addition to this, there is a mutual coupling between them. Now, whenever there is a mutual coupling between two things, what do? You always put these blobs. What does it mean? It means that if the current is flowing into the blob in these two directions, then they would be additive, magnetic fields will be additive. If the currents flow in the opposite directions, that means in one it goes through into the blob, and in the other one it goes this way, that means it goes out of the blob, then they are subtractive. After all, that addition or subtraction does what? It adds to or subtracts from the total kinetic energy that is stored in these two. So, this change should be reflected in some kind of a change in the kinetic energy. Okay. So, the kinetic energy, if if this is not there, the kinetic energy would be written as half, let us designate the two coordinates, then half L1 Q1 dot square plus half L2, here it is Q1 minus Q2, Q1 dot minus Q2 dot square, in the absence of this mutual inductance, right. Now, if the mutual inductance is there, if the mutual inductance is additionally there, then you see due to the Q1 it is going out of this blob, and the Q1 minus Q2 is going into the blob. Okay. So, how will we designate this? The amount of additional energy stored in the inductor is half m, the two i's I1 I2, right, you know that. So, the additional kinetic energy would be plus half mutual inductance, half m Q1 dot into Q1 dot minus Q2 dot. Wait, now here I will first put plus minus and then do the choice. This is the amount and then we will do the choice. Now, you see, because I have put the dots here and here, Q1 goes out through the dot and Q1 minus Q2 goes into the dot, therefore, these two currents are subtractive. If it is subtractive, I have to take the minus sign. Okay. The rest remains the same. All you need to do is to do this. Now, if I change the position of the dots, say this one is moved to here, obviously you can see that this will be additive, we have to take plus. And when you are actually doing this in problems, then you have to take that into account somewhat minutely, so that many people I have seen make a mistake in the signs here, because this is, see, if these are two independent coordinates, there is no problem, but because these are two related, Q1 minus Q2, that is why, I do not know why, but students tend to make mistakes. So, be careful about that. If you are taking Q1 minus Q2, it is going into, if you are taking Q2 minus Q1, it is going out of. Fine, then you can continue with this.
So, what is the mechanical equivalent of this?
Mechanical equivalent of a mutual inductance. No, mechanical equivalent of a mutual inductance, tough question. But there can be, and that this question I will come to about a month later, when the required background has been built up. At this moment I will not get into this, because that will require a lot of things to be told. I will come to that later. But keep this question in mind, and when the time comes, raise it again, okay, and you will really see where it comes. So, what is the mechanical equivalent of a mutual inductance? We will come to that. Okay, thank you very much today.